Welcome to Learning Machines seminars at RISE, and especially welcome to Martin Willbo, who is today's speaker. Martin joined RISE a few months ago. Before that, he did his master thesis, defended this at Chalmers, regarding time series with privileged information. Today's topic is going to be few-shot learning for sound event detection. And the floor is yours, Martin.
Okay, thank you, Olof, for that introduction. So in this seminar, I will give a presentation on few-shot learning for sound event detection, which is an area that I have been studying for the last couple of months. And I want to start this presentation off by briefly introducing some of the topics that we will go through. So first, I will give a brief introduction to few-shot learning and what few-shot learning is, how you define few-shot learning problems. I will talk about what sound event detection is and how we can see sound event detection as a few-shot learning problem. And I will also discuss why few-shot learning is relevant for sound event detection to start with. And when we have done this, I will introduce some basic and simple approaches for how one can do few-shot learning for sound event detection. And I will then finish this presentation by introducing some ideas and research questions for improvements that me and my group at RISE have. So let's talk a little bit about the motivation of why we would like to do few-shot learning for sound event detection. So when it comes to soundscape analysis and bioacoustics, for example, it is relatively easy to gather large amounts of data. You could, for example, strap a passive recording device to a tree in some forest or spend a couple of days out in the field gathering recordings. And it is not uncommon to have these audio data sets with recordings spanning several months. What is difficult and extremely laborious in this setting is to actually annotate the data. It is quite impractical to sit and listen through several months of audio recordings, and this annotation process is typically not something that you could crowdsource either, since actually properly annotating this data, in example, bioacoustics, requires a large amount of expertise and domain knowledge. So for many of these areas for which we would like to do some machine learning applications in bioacoustics, for example, we need to be able to learn from a few examples because we are only going to get a couple of labeled examples. So that is why we are interested in few-shot learning for sound event detection. And a little bit about the research field of few-shot learning. So few-shot learning methods and techniques are not exactly new. They have been relatively extensively studied from a vision perspective. It is, for example, quite easy to find a lot of literature for few-shot learning on, for example, image classification. But few-shot learning has now also started to make an appearance for soundscape analysis and sound event detection problems. But at this current time, it is quite common to employ similar techniques for sound event detection as it is for image classification. So if we have some technique that is working quite well in image classification, well, then this technique is usually applied without any major changes for sound event detection as well. And I also briefly want to talk a little bit about the DCASE challenges and the DCASE organization, which is a community which aim to further the research in soundscape analysis. So if you find this talk interesting, I encourage you to check that community out, since they are a driving force for soundscape analysis at this time. And with that out of the way, let's talk a little bit about what few-shot learning actually is. So essentially, few-shot learning are tasks in which we would like to make predictions for some data points based on just a few set of labeled examples as the training data. And these few-shot learning tasks are usually described by these following terms. They are k-shot, n-way, support set, and query set. And I have provided a clarifying figure here on this slide. So we have this support set, which is this blue rectangle, and this is the labeled data that we have to our disposal. And in this case, this support set consists of 3 different classes, where each class have 2 examples each. So this then would be a 3-way, 2-shot, few-shot learning problem. And now we have this query set in this green rectangle here. And this is the data points for which we would like to make predictions about, given the information in the support set. And something to note here is that the support set is the training data we have at our disposal for this few-shot learning task. So we have very little training data in these problems. Okay, so what is sound event detection, and how can we see sound event detection as a few-shot learning problem? So in sound event detection, we have some audio file, some audio signal as our input. And this is represented here by this waveform in the figure on the slide here. And what we typically do in sound event detection is we take this audio signal and divide it up into smaller audio segments. So our file is now a large amount of consecutive smaller audio segments. And in this few-shot learning task, we have been given some we have been provided some events. That is, we have some annotations of some timestamps where the event we are interested in are taking place in this audio signal. And then we take the audio segments which fall between the timestamps of these provided events, and then those audio segments then constitute our support set for this few-shot learning task. The rest of the audio signal here in this blue square here is then the query part. This is the part of the audio for which we would like to make predictions. That is, we want to take an audio segment from this query part and classify it as either containing the event we are interested in or not. And by doing this, we then get as output some event predictions. We have some event onsets and offsets based on this. And we do this prediction with a few-shot sound event detection system. And what is a few-shot sound event detection system then? And here there are many different approaches with respect to which model you use and what algorithm you use to train your model, etc. But for this talk, I will focus on a very basic and common approach with respect to both model and algorithm, and that is prototypical networks, which come from a paper titled Prototypical Networks for Few-Shot Learning, which was published in 2017. Okay, so what is prototypical networks? The main idea behind prototypical networks is quite simple. And that is that we have some embedding function f, which typically is some convolutional neural network. And we use these embedding functions to embed the data points in our support set into some embedding space. And after we have done this, we create prototypes for each class in the support set by averaging over these embeddings. And this is described here by the first equation on this slide. So we have some prototype C, K, that is, we have some prototype C belonging to class K, which equals the sum of the embeddings for the data points in the support set belonging to class K. Then we just divide this by the number of examples of class K in the support set. And we do this for each class, and that then are our prototypes. And given these prototypes and some distance function d, we can then produce a distribution over classes for some query point x. So we get a probability distribution for some query point X belonging to some class K by taking the exponential of the negative distance of this query point in the embedding space to the prototype for class K. And then we divide this by the sum of the exponential of the negative distances of this query point in the embedding space to all the prototypes. So this is essentially a softmax function. And some intuition behind this is that if our query point X has a small distance to some prototype K and a large distance to the other prototypes in the embedding space, well, then this query point belongs to the class K with a high probability. And I have provided some clarifying visualizations of prototypical networks here. So in this case, we have a support set with 3 different classes. We have a green class, an orange class, and a blue class. And for each of these classes, we have 5 examples each. And as you can see here, we average the embeddings of these examples to get our prototypes. So we get 1 prototype for each class, here represented by the black dots C1, C2, and C3. And then we have this query point X, for which we would like to make a prediction in this embedding space represented by the white dots. And we measure the distance for these query points to all the prototypes in the embedding space. And for this case, it happens to be so that the distance to the prototype representing the orange class is smallest. And therefore, we, in this instance, will classify this query point as belonging to the orange class. And the distance function typically used for prototypical networks is the Euclidean distance. And then training of these prototypical networks is done by minimizing the negative log probability of the true class K. So this is the equation here at the bottom of the slide. We have some loss function J, which is the negative logarithm of this probability distribution, which I described on the previous slide. But we minimize this essentially by reducing the distance of the query point to the prototype which it belongs to, as well as increasing the distances of these query points to other prototypes. And before we move on, I would like to touch a little bit upon what features we typically use in sound event detection. And the most commonly used features in sound event detection and other soundscape analysis tasks as well is something called a MEL spectrogram. So what we do is we take our raw audio signal and we pre-process this into MEL spectrograms, which then are the features we use during training and testing of our networks. And this is a feature which is suitable for almost all soundscape analysis tasks, and the intuition or motivation behind why we use MEL spectrogram is that these are inspired by how humans perceive sound, and this seems to work very well for many soundscape analysis applications. Okay then, so now we have some grasp of a typical approach, some model for the typical networks, which we can use for sound event detection. Then the question is, how do we actually train this embedding function? How do we train our network? Since remember that we only have a very limited amount of labeled data. This support set can consist of as little as just 1 labeled example per class of interest. So it is usually impractical or borderline impossible to actually fit deep models on such limited data sets, and we need some way or technique to overcome this limitation. And one very common way of doing this is lean on some transfer learning technique. And what we do for sound event detection is that we introduce a larger data set, which we have annotations for, which I will call the base data set, and we pre-train our embeddings on that model data set, and then we reuse the learned embeddings for the downstream task of few-shot learning. And there are different ways of doing this, and one family of methods is called meta-learning. And the goal in meta-learning is to learn to learn. And what this essentially means is that we want to train our model in such a way that it generalizes well to previously unseen classes, given just a few examples of these unseen classes. In other words, we can say that we want to train our models in such a way that it generalizes well to the downstream task of few-shot learning, because that is essentially what it is. So we introduce a base data set, and then we do some meta-learning algorithm or meta-learning technique for the actual training. And one very common meta-learning scheme is something called episodic training. The main idea behind episodic training is essentially that you, during training, create a large amount of few-shot learning tasks, with the intuition being that if we train our models on few-shot learning tasks, well, then they generalize well to the downstream task of few-shot learning. And I have outlined the general idea of episodic training here. So in the first step, we have our base data set, which with a large amount of classes, which I here have represented by these different colored squares. The first step then is to randomly select a subset of these classes in the base data set. And for this illustration, I have chosen 3 classes on random from this base data set, which I will then use in the following step. And this following step is then to, from these 3 classes, randomly select a couple of examples, and then have these examples then constitute a support and query set. And now we essentially have a few-shot learning problem. We do a forward pass, we get some loss, and we backpropagate and update the parameters of our model. And then we do this over and over again. We continue training in this way, creating few-shot learning tasks until some stopping criteria is met or we are pleased with our model. And then we reuse the learned embedding for the downstream task of the few-shot learning task done. But meta-learning is not the only way to do few-shot learning, both for image classification or sound event detection. A different approach, which might be very familiar to you, is just do a whole classification, just train a classifier on the base data set. So this is essentially just regular supervised learning, supervised training of a classifier. And the idea is then, when you're pleased with this classified training, to reuse the learned embedding function for the downstream few-shot learning task. I want to touch a little bit upon which method one should use for few-shot learning in sound event detection. Should you go with a meta-learning scheme such as episodic training, or should you do something simpler such as training a classifier on the base data set? And this is a question which is quite hard to answer, actually, since there generally is a lack of comparison for these different learning methods, especially when it comes to sound event detection, where this is an area which is quite understudied overall. I can, however, say that for image classification, there are instances when doing this whole classification instead of some meta-learning scheme results in comparable or better results. Something of note, though, is that for this DCASE 2021 Task 5 challenge of few-shot learning for sound event detection, none of the leading submissions was built upon using simple whole classification. Many of the leading submissions in that challenge was built upon prototypical networks and episodic training. Okay, then. So now we have talked a little bit about how our models look and behave and how we train them. And now it is actually time to use them for this downstream task or the actual few-shot learning. This is sometimes called metatesting. And we start by first using the pre-trained embedding function to create a positive prototype in the embedding space from examples in our support set. And as we went through earlier in sound event detection, this support set then is the audio segments of this input audio file, which falls between the timestamps of the provided events. So we create a positive prototype from audio segments containing the event we are interested in. But we also need some way of classifying a query segment as not containing our event. And we do this by creating a negative prototype. So we have a prototype in this embedding space representing not the event we are interested in. And one common way to do this actually is to just average over the whole audio file and create our negative prototype that way. And this is built upon the assumption that the event we are interested in is quite scarce in this recording that we have as inputs. And in practice, this assumption seems to hold true. This seems to be quite a good way actually to create this negative prototype. There is not a lot of performance gained by randomly selecting a smaller subset of the file. Now when we have this positive and negative prototype, we can start embedding our query segments into the embedding space and measure the distance to these two prototypes then, and based on this, classify this query segment as either containing our event or not. And by this then, in the end, we have an output with predicted event onsets and offsets. I have again provided a clarifying visualization of this metatesting stage, where we, based on our provided events here in this green rectangle, have created a positive prototype in our embedding space. This is the green dot. We have created our negative prototype by averaging over the whole input file, the whole audio input signal. And this is then represented by this red dot in our embedding space. And for some query segment, here represented by this blue rectangle, we get some point in the embedding space and we measure the distance. And in this case, this blue dot is closer to the green dot, and therefore we will classify this query segment as containing the event we are interested in. So I want to talk a little bit about post-processing of predicted events as well, since this is a very common step in few-shot learning for sound event detection. So I have in this slide included 3 different techniques. They are medium filtering, fill gaps, or this is also sometimes called smoothing. And then we have remove short duration events. The first 2 methods, medium filtering and fill gaps, can essentially be seen as removing short spurious events from our predictions, or in essence, removing noise from our predicted events. And the remove short duration events is inspired by the following example. Say that we in our support set, our provided events, we can say that they on average have a duration of, for example, 1 second. And if our then predicted event have a length of 0.1 seconds, well, then this is not very likely to actually be an event, since they on average are much larger. And doing these post-processing techniques is something that leads to greater performance in this sound event detection task. So leaving this step out is for now not something that is done at all. Before I move on entirely, I want to touch a little bit upon some modern approaches to few-shot learning for sound event detection. What techniques and methods people use nowadays to get greater performance. And these modern approaches are from considering the submissions of this DCASE 2021 Task 5 challenge. And something that can be seen is that using larger networks and different architectures than originally considered in the paper from 2017 can lead to greater performance for these sound event detection tasks. And larger networks can, for example, be deeper convolutional neural networks, and different architectures could, for example, be using a ResNet instead. Data transformation or augmentation techniques such as spec-augment is also very commonly used. Spec-augment have seen very much used in, for example, speech recognition, where this augmentation technique leads to greater performance. And this seems to be the case for sound event detection tasks as well. And in this figure here, we can see some of the augmentation that spec-augment does. So we have our input feature, our mouse spectrogram, and spec-augment then essentially filters or zeroes out some frequency bands and some frames in time. And the hope is then to make our model learn better and be more robust. Attention similarity models is also something that is used, and this is motivated by the fact that our audio segments or mouse spectrograms can, for example, represent audio that is 1 second in length, but our events might take place in shorter amounts of time. Our events might, for example, have an average length of 0.2 seconds. Then including some attention in the model might help guide it to the parts of the inputs that is relevant for what we are interested in, and that is recognizing the events. And this is not an extensive list of modern techniques and approaches to fusion learning for sound event detection. And if you are interested in learning more about what is currently done, I encourage you to check this DCASE community out. Okay then, so now I will talk a little bit about some research questions and ideas that me and my group at RISE have regarding few-shot learning for sound event detection. And one of them is working with unlabeled data. As I said earlier in this presentation, it is quite easy to gather these large amounts of data. Just gathering large amounts of audio recordings is very easy, but we can't make use of very much of it in supervised settings since we don't have any labels for it. So we would like to include it in some way during training, and that leads us to looking into some self or semi-supervised few-shot learning techniques for sound event detection. And one such idea could be something that we call unlabeled prototypes and queries during training. And this idea essentially is that we first randomly select some locations in the audio signal, which here is represented by the blue, pink, and green rectangles. And at these locations, we take a number of consecutive segments to constitute a support and query set. So for example, at the location of this blue rectangle here, we select 10 consecutive segments, and we let the 5 first of those be a support set, and the following 5 be query points. Then we use this as examples of additional classes during episodic training. And this builds on a quite common assumption in contrastive learning, that is that neighboring data is usually quite similar. So for example, in an audio recording, if you have rain 1 second, then it will probably rain the next second as well in this recording. And one potential benefit of using these unlabeled prototypes and queries during training is that it is possible to potentially make the embedding function sensitive to the characteristics of the test environment, since we do not rely on labels for this technique. So we can include data from our test environment during training. And I have provided some preliminary results of this idea in this figure here. So on the y-axis, we have an f-score or f-measure, which we use to measure the performance of our models, and higher is better. And on the x-axis, we have results for two backbones, where backbone 1 is the convolution neural network originally in the paper from 2017, and backbone 2 is a ResNet 18 model. Then we have these blue and red bars, where the blue bar represents just supervised episodic training, and the red bar represents the idea I presented on the previous slide. And even though these results are preliminary, and this is very much a work in progress, it seems that doing this semi-supervised training or using these unlabeled prototypes and queries during training can increase the performance of these sound detection models. And some other points of interest in our group is quantifying the impact of model definition and test time. And what I mean by this is that we would like to investigate and quantify which impact on performance the choice of examples to use when constructing these positive and negative prototypes have. So for example, is there a good way to choose examples from this audio file to constitute a negative prototype? Can we do differently than one negative prototype? What if we have many, for example? And quantify a little bit about what impact on performance these have for these sound event detection systems. We are also interested in looking into what impact the prototypical loss function have on supervised and semi-supervised training of these prototypical networks. Are there strengths and weaknesses? How can we mitigate them, etc.? And something of interest is also looking at alternatives to meta-learning schemes. As I said previously, comparisons between these meta-learning schemes and, for example, whole classification is a relatively understudied area, and we find it very interesting to dig a little deeper there. And some ending notes from our presentation is that sound event detection, or future learning for sound event detection, is quite a difficult and quite a novel problem. And if you think this presentation was interesting, I encourage you to check out the DCASE challenges once again. And if you want to talk future learning for sound event detection, feel free to contact me. I would love to have that discussion with you. And with that, I would like to say thank you for listening. Thank you.
Thank you, Martin. Do we have any questions for the speaker? Perhaps I can start with one. You mentioned the prototypical network training, and then you mentioned that you can pre-train your embeddings using classification, for example. Do you know any other methods of doing this first step of the training?
Yeah, I know some other meta-learning techniques. And one of them, for example, is to train a model in such a way that it initializes some weights for some other model, in some sense based on the support set, which then is used for the sound event detection, for example. This is not a technique which I have looked very much into, but I know that it exists. And there are some other techniques which fine-tune parameters based on this support set as well. I can't say very much about them.
I suppose you could use other kinds of unsupervised pre-training as well.
You definitely can. I think giving some consideration to what good pretext task for self-supervised training for this problem could be is very interesting. Something I haven't tried myself is, for example, leaning on what people are doing for images, where we, for example, take one image, or in this case, one audio segment from this file, and do some transformations and looking at contrastive loss, for example, as a pre-training task.
Mm. Martin Nilsson asks in the chat if you can suggest a good recent review of meta-learning methods.
For sound event detection, I cannot. Actually, I haven't found one. So if anyone find one, please send it to me as well, because I have had a large trouble with actually finding some comparisons, good comparisons for these different techniques for sound event detection. It seems to me that everyone more or less just do this episodic training, for example, and that is all you can find, more or less.
Mm. Would there be any reasons for this? Is it, for example, is it difficult to evaluate?
I don't think so. I mean, if you have the other method implemented, I suppose you could quite easily compare it to some meta-learning technique, at least based upon your score, for example.
Mm.
However, comparing intricacies might be more difficult. For example, I mean, characteristics of the learned embeddings and so on.
Mm.
I have a question.
Yes.
I was thinking about the stuff you were saying about using this self-supervision for sort of test data, and that it seems to help with the results as you show. But I was wondering if maybe you could do also. So you could also think of that you have like 3 data sets. So one is like your supervised training data set, and then let's say you have some other data which is unlabeled, but which is sort of considered training data in a sense, even though it's unlabeled. And then you have a third set, which is the actual test set. And I was just wondering if you have also seen what happens for the test data if it doesn't see the test data at all, because sometimes, I mean, it can be argued that even unlabeled test images maybe should not be part of the training process, if that makes sense.
I mean, yeah, I can see your concern there, that perhaps even unlabeled data shouldn't touch our training, but I can reveal a little bit more information about the figures I had something here. For this example, for Backbone 2, there is actually no unlabeled data from the test environment here. So
okay, nice. Yeah. So, but I also think that there are cases where I mean, it makes sense that in some cases you would refine your model for test data. It depends a little bit on context and so on, I guess. But yeah, but it's good that you have also tried without any test data, so to say.
Yeah. So I mean, there are a lot of parameters to tune here when it comes to training these models, but in this case, we have not done any semi-supervised training on the test data. So yeah.
Yeah, and another question that I have, when I hear the overview somehow of these prototypical networks, sort of the intuition that I get from it is that it just sounds like some sort of nearest neighbor with features or something like that. I mean, is there anything more to that paper than kind of just nearest neighbor, if it makes sense? I mean, what more does it do?
I mean, can't really give you a straightforward answer to that, but I can see where you're coming from, and I would suppose that this paper is probably inspired by just an approach such as k-nearest neighbors.
Yeah. So, because I think I got a little bit confused. So kind of the relationship between. So you had a prototypical network, that was one part, and then you have this whole set training of features. And you compare that to the meta learning thing, but do both? I mean, does the full set training and meta training are both of them compatible with prototypical networks? If you get my question, or
okay, yeah. So yes and no, I suppose. I mean, the thing you do is that you reuse the learned embedding function, and with this, you could definitely create prototypes, right? And this is what is done during the testing stage in both cases. But during the whole classification training, well, then we have no prototypical network loss, for example. Then we used to cross entropy loss, for example, on the base data set. But we reuse the embedding to create these prototypes at test nonetheless.
Okay, yeah, thanks.
But when you speak about prototypical networks, that typically includes the prototypical episodic training.
Yeah. So when you normally mention prototypical networks, these include a prototypical network loss and episodic training.
And that is something above the nearest neighbor, I think, isn't it?
Might be.
I guess the one difference is that here you're actually you have the embedding space calculated together with the nearest neighbor thingy. So you do it end to end, so you learn to separate it. I guess that's the difference from just taking the embedding space and doing nearest neighbor. Isn't that kind of the whole point of contrastive learning, is to kind of separate spaces like this? So
yeah.
So the trick is how do you separate them? And I guess one is to do nearest neighbors.
Yeah. Seems right to me.
Are people looking at it?
Yeah,
yes,
so kind of
sorry.
So one follow-up to that is I mean, it was quite popular a few years ago to do Siamese networks and to do triplet loss on Siamese networks. But I tried to find it now when I search for it, but I seem to remember some paper a while ago that added some simple multilayered perceptron between the twins so that you didn't need negative samples. Is that something you recognize or even remember? I don't even remember where I read the paper or what it could be called, but
so I am quite new to this field overall, and there's a lot of things I don't know, and this approach does not seem familiar to me at all, so I have not heard anything about it. I'm sorry.
Okay. Okay. I mean, it could be interesting otherwise, because I think, I mean, a lot of the issues, at least in my experience with these contrastive methods, is that how do you find negative samples? I mean, that's the tricky part. So if you somehow magically can kind of model your way out of that problem, that would be super interesting. But it also sounds too good to be true, to be honest. But
yeah.
All right. Thanks.
But you can also assume your way out of it by assuming that most of the data here will be something that we are not referring to as an event, which is what Martin talked about.
Yeah. But even so, there could be some interest in actually making this choice a little bit more principled than just averaging over the whole file. But how to do it is another question entirely.
I mean, you can kind of fiddle around. I mean, depending on the task. I mean, in this case, maybe averaging is a good approach, but like a general learning approach, I mean, of course, you can fiddle around with it, but usually, I mean, it's always a balance between kind of fiddling with a model, so you're not overfitting on some samples if you happen to get negative samples as part of your positive sample set, or vice versa. And if your model is too expressive, it will be able to detect that anyway. So, I mean, if you can have some principled approach in terms of the modeling, that would probably be good, I think.
Yeah, it might be. Yep.
Are there alternative ways of measuring the similarity in the nearest neighbor the measurements, the similarities. You mentioned that you use the Euclidean distance in the prototypical networks. Could you do it the other way?
I mean, there are some previous works mentioned in the prototypical network paper where, for the example, they use cosine similarities and such. But they also found that for prototypical networks, Euclidean distance is the best way to measure similarities. And this is based on it being a Bregman distance in some way, a Bregman measure.
Okay, and let's thank the speaker and welcome back next week. We'll have Maria Prisalu from Lund University. She's going to talk about semantically reasoning pedestrian models in generative autonomous vehicle testing. So welcome back next week. And thank you, Martin.
Thank you.